Hi, in this section, we're going to apply the idea of implicit differentiation in what we call a related rates problem. So related rates just means that more than one rate of change is going on. So there's more than one thing changing with respect to the variable time. So we'll use t for time. And the steps that we're going to use to solve the related rates problem is first draw a diagram. Diagrams are really helpful. And then identify the variables that you're going to be using. So the typical variables would be h for height, l for length, those kind of things. You need to identify what you know and what you need to find. Once you've identified what you need to find and all the information that you have, you're going to write your equation, okay, using your variables. So this is where we're going to use implicit differentiation. We're going to differentiate the equation with respect to the variable t for time. Once we've differentiated, then any known values will substitute in, but we don't do that until we've differentiated. Okay? So since we're going to be finding a rate of change, you need to be careful. Is it an increasing or a decreasing rate? And then last, this is not a formal check, but you should check to make sure you have proper units and that the solution that you get is actually feasible. Does it make sense? So let's look at this first example. Grain is pouring out of a silo and it's forming a canonical pile. So that just means the shape of the pile looks like a cone. So you would have some grain coming out of the silo and it's forming this pile. There's my sad pile, which is in the shape of a cone. So the radius is always twice the height. So I know that the radius is always equal to 2 times the height. I also know that the grain falls at a rate of 2 cubic inches per second. So that would be a volume, cubic inches. And it's a rate that the volume is changing with respect to time, which would be dV dt. That would be 2 cubic inches per second. So the question is, how fast is the height of the pile changing? So we need to find dH dt, which is the rate that the height is changing with respect to time. And I need to do that when the pile is 4 inches high. So that would be when h is equal to 4. So since the shape of this pile is a cone, I'm going to use the volume formula for a cone, which is 1/3 pi r squared h. So I'd like to simplify this equation as much as possible before I take the derivative with respect to time. So I know that the radius is always 2 times the height. So I'm going to substitute for r to h, and we're going to square that. So let's clean up this formula. The 2h squared becomes 4h squared. So my constant would be 4/3 pi, and this becomes h to the third. So this is a much nicer volume formula. Now that I've cleaned everything up, I'm going to go ahead and implicitly differentiate with respect to the variable t. So if I take the derivative of the volume, it's going to be dV dt. The 4/3 pi is constant, so it stays. The derivative of h to the third with respect to the variable t is going to be 3h squared times dh dt. I can see that these 3's will cancel. And then at this point, what I need to do is I need to substitute some known values in. Well, I know that the volume changes at 2 cubic inches per second. So I can replace dV dt with 2. And this would be 4 pi. I'm supposed to figure out how the height is changing when the height is 4 inches. So I can replace h with 4 and square that. So all that I have left to find, sorry, this is supposed to be an h, all I have left to find is dh dt. So the 4 squared is 16 times 4 would be 64 pi. If I divide both sides by 64 pi, then I have my dh dt. Okay, so again, we figured out what our variables were. We listed what we have, what we need to find, and then we had to come up with an equation. Since this pile is in the shape of a cone, I used a volume of a cone. Once I simplify the equation as much as I can, then I took the derivative with respect to the variable t for time. Because that's what I'm given. I'm given a rate of change for the volume, and I need to find the rate of change for the height. Okay? So I needed to get this in the form of derivatives or rates of change. And then I substituted in quantities that I knew. I knew how the volume changed, and I knew that the height had to be 4 inches. So simplifying this fraction, I get 1 over 32 pi. That would be how the height is changing, okay, when the height is 4 inches. Notice that this is a positive value, and you could plug this in to get a decimal approximation. This answer makes sense. Okay? So typically what we do with word problems is we write a sentence answer. So the height is increasing because this is a positive 1 over 32 pi. So the height is increasing at a rate of 1 over 32 pi inches, because it's height, right? The unit is just inches per second. Okay, so that's it for this related rates problem. Let's look at a value the x, the y, and the z actually stands for. Example. So we're going to do 3 examples all together. In this next example, we're looking at 2 cars. They're leaving a parking lot. One is traveling north and the other is traveling west. So the question is, at what rate is the distance between the vehicles changing 30 minutes after they leave the parking lot? I'm going to draw myself a diagram. And because my directions here are one car is traveling north and the other is traveling west, I'm going to use a north, south, east, west diagram. So one car is traveling north and the other one is traveling west. What I'm trying to find is how the distance between them is changing. So I'm trying to find this green line, the distance between these 2 cars. So if you look at this geometric shape, this is the shape of a right triangle. So what I need to do is I need to assign variables for the pieces of my graph. I think I'm going to let x be the car that's going northbound. So whenever you use variables that are generic, like an x, y, z, you need to state what they are. If you're using L for length or V for volume, you don't have to have a let statement because those are variables that we all know what they mean. But I don't know what my X stands for, so I have to state that X is going to be the northbound car. And then Y is going to be my westbound car, or however you want to write this. Oops. And then the distance between them, I think I'll call that Z. So Z is going to be the distance between the cars. And these don't, your description doesn't have to be a complete sentence, but you want to know what, oops, sorry. Okay, so we have the speed of the north and the west traveling cars. So we know that the rate, which is its speed, dx dt, our northbound car is traveling at 20 miles per hour. So that would be its rate. And the westbound car is traveling at 18 miles per hour. So dy dt is equal to 18 miles per hour. What we have to find is the distance that the rate is changing, the distance between the two cars. So we need to find dz dt. Now, since this is a right triangle, it seems logical for me to use the Pythagorean formula, right? So I can use that x squared plus y squared is equal to z squared. And this is my equation that I would have to implicitly differentiate. Okay, so we're going to take the derivative with respect to x, y, and z, right? Or with respect to t. So the derivative of x squared is going to be 2x dx dt plus 2y dy dt. That's going to be equal to 2z dz dt. So I know dx dt and I know dy dt. So I can substitute those values in. I need to find dz dt. So something else you could notice is that you can divide both sides of this equation by 2 and get rid of that constant 2. So let's go ahead and clean this up. Since dx dt is 20, this becomes 20x plus dy dt is 18. So this becomes 18y is equal to, I don't know what z is, but I can find it because I have a right triangle. So let's go back and look at our problem. It says we're supposed to find the rate that the distance between the vehicles is changing 30 minutes after they leave the parking lot. So I need to find x, y, and z 30 minutes after they leave the parking lot. So if they've only been traveling for 30 minutes, then the length that the car X has been traveling is 10 miles, right? And then car Y has been traveling for 9 miles. So to figure out what Z is, I just have to use my Pythagorean formula that 10 squared plus 9 squared is going to be equal to Z squared, which would be 181, or the square root of 181. That would be my Z value. So I know x, y, and z. I can substitute those values into my equation to have 20 times x, which is 10, plus 18 times y, which is 9, is equal to z, which is the square root of 181 times dz dt. At this point, it's just a matter of getting dz dt by itself. So we're going to have 200 plus 162, which would give me a 362. And then I would divide by the square root of 181 to get dz dt by itself. So this is how the distance between the cars is changing. If I rationalize that denominator and simplify, I get 2 times the square root of 181. So I'm giving the exact answers for these problems, but you could just as easily put this in a calculator to see if the answer is reasonable. Okay? And this is a reasonable answer because as the cars go further and further away from each other, the distance, the rate that the distance is changing would be an increasing distance. So having a positive answer makes sense. So my sentence answer would be the distance between the cars can't spell, cars, is changing or increasing, at a rate of 2 times the square root of 181 miles per hour. All right, so again, draw a diagram, identify your variables, figure out what kind of equation you need to use, and the equation that you're going to use is modeled by your diagram. Write down what you have and what you need, then take the derivative, substitute in the values you know, so all that's left would be just your rate of change that you need to solve for, and then make sure that it's a reasonable solution. Let's go on to our last example. So let's say that we have somebody observing the launch of a hot air balloon, and they're standing 100 meters away from the launch site. So I'm going to go ahead and kind of draw what this looks like. Okay. We have somebody on the ground, and they're watching this hot air balloon being launched. There's my balloon. Okay. And here's our person. So this is the person observing the balloon. Okay. So the balloon is rising from ground level and it's traveling vertically at a speed of 3 meters per second. So we need to know how fast the angle of elevation is changing 20 seconds after the launch. So the angle of elevation is this person looking up. So we have to figure out when this angle, how fast this angle is changing. So I'm going to call this theta. I'm going to let theta be the angle of elevation. Okay, so I do need to find that. What do I have here? I have the distance along the ground is 100 meters, and that's a constant distance. It's not going to change. What's changing is theta. I do know the vertical speed, so maybe I'll call this h for the height of the balloon, and that would be vertical speed of 3 meters per second. So I know that the rate at which the height of the balloon is changing with respect to time is 3 meters per second. So I need to set up an equation. Going back to your trig, we have an angle. We have the side adjacent and we have the side opposite. So that would be tangent where you have opposite adjacent. So I know that the tangent of theta is going to be equal to h over 100. And now I need to take the derivative. There is no other way for me to simplify this equation. The only thing I could possibly do is maybe multiply 100 to both sides and get h by itself. But that's not a big deal right now since it's just the 100 is a constant. So if I were to differentiate with respect to time, okay, the derivative of tangent of theta with respect to time would be the derivative of tangent, which is secant squared theta, but then we have to times this by d theta dt, because remember we're using implicit differentiation. And then h over 100 becomes, the 1 over 100 is constant, the derivative of h is just dh dt. So that actually wasn't that bad. Okay, so I need to find the rate at which theta is changing. I'm going to move the secant squared theta over to the other side, and this becomes d theta over dt is equal to 1 over 100. And now remember, the height is changing at the rate that the height is changing is 3 meters per second. So that's 3 times cosine squared theta. Dividing both sides by secant squared means I could just write cosine squared because that's the reciprocal of secant. Let's simplify this a little bit. I have d theta over dt is equal to 3 over 100 cosine squared theta. Okay, the problem is that I don't know what cosine squared theta is. So going back to our original example, we want to know how fast the angle of elevation is changing 20 seconds after the launch. Okay, so this is what we need to find. And it would be 20 seconds after this balloon is launched. So let's go back to our diagram. So I need to figure out cosine squared of theta. In this diagram, cosine with respect to theta would be adjacent over hypotenuse. So I need to add in the hypotenuse, which would be 100 squared plus h squared. Maybe I want the h squared plus 100 squared. And then you would take the square root. So cosine of theta is going to be equal to 100 over the square root of h squared plus 100 squared. And we could figure out what h is because we know this is 20 seconds after launching and we know the speed that things are changing. Okay. So that would give us 60 for h. Okay, so again, the height is changing at 3 meters per second. 20 seconds after the launch, the height would be 60 meters. So substituting in 60 for h, we have that cosine of theta is equal to 100 over 60 squared plus 100 squared. But and I'm sorry, that would be cosine, but remember, we don't want just cosine of theta. We want to figure out what cosine squared of theta is. So cosine squared of theta, if I square both sides, it's going to give me 100 squared over 60 squared plus 100 squared. And that simplifies to 25 over 34. So cosine squared of theta is 25 over 34. And now I can plug that back into my equation. So d theta dt is going to be 3 over 100 times 25 over 34. And then after simplifying, that should be 3 over 136. So the angle is changing at 3 over 136. What are the units when we talk about angles? So we only have two types of units with angles. We have degrees and we have radians. If theta is not given as degrees in the problem, you assume it's radians. So notice in this problem, theta was not given as degrees, so we assume it's radians. And the angle of elevation is increasing, right, as the balloon goes up. So we would write that the angle of elevation is increasing, and it's just a coincidence that the problems that I chose to do have increasing rates. If it came out to be negative, then it would be a decreasing rate. So the angle of elevation is increasing at a rate of 3 over 136 radians per second. So we would write, rads per second. So that would be about 0.02. That makes sense. If I was to switch that to degrees, it would be about 1.3 degrees per second. So that makes sense as well. So hopefully these 3 different types will give you enough examples to be able to tackle all these related rates problems in this section.